So this question here, we see two objects headed toward each other. We see them colliding and sticking together. So right off the bat, we see an inelastic collision, which means the kinetic energy not conserved. This is a sticky collision. Okay, so what we have here is we have data. And so we have a student conducting an experiment to verify whether momentum is conserved. Okay, so that's just conservation of momentum. Two objects travel toward each other. Two objects travel. Data collected from the three trials are shown in the table. Which of the following statements is correct based on the data? So the first clause in each one of these is conservation of momentum can be verified, cannot be verified. Can and cannot. Cannot be determined. So we have to first find out what's going on with this case. So we've got three trials. We have mass of the object before, which we can see is 2.1, 1.9, and 2.0, which will average out to 2.0 plus or minus 0.1. It's worthy to note that that uncertainty is about 5%. 0.1 out of 20 is the same as 1 out of 20, 5%. The mass of object y, we see a similar thing, 0.9, 1.0, 1.1 is going to average to be 1.0. But the uncertainty here is going to be 10%. The speed of object x beforehand, we have 2.0, 2.1, 2.1. So I think that the average value in this case will be about 2.066. And we have about 5% uncertainty again. The speed of y afterward, we could see it's 1.0, 1.0, and 1. That's going to give us a mean of about 1.033. And we have about 10% again. And the speed of the system after the collision. So that's the two combining together. We have 0.9 and 1.1. And we average those out. And we're going to get about 0.966. And again, we're looking at about 10%. All right, so P0 equals P. So we've got mass of the first one, which is about 2, times its velocity beforehand, which is about 2, and the y, which is a mass of about 1, and its velocity, which is minus 1, because it's headed in the other direction. These are all minus. Will that equal the nu, which is a mass of 3, and its velocity of 1? So we have 4 plus a minus 1 equals 3. So we have 3 equals 3. So it looks like it's conserved. Now, when you look at all of the uncertainties that are here, in this first momentum, we have a 5% uncertainty and a 10% uncertainty. So we've got 15% uncertainty here. And we have 20% uncertainty here. And we have about a 20% uncertainty here. And so that 20% uncertainty means 3 plus, it's going to be 3 plus or minus about 0.6. So 3.6 down to 2.4, 3.0. The point in that is that if we ran this for all three different trials versus doing the average, we are not going to get any, and we don't get any values outside that range. So the momentum can be verified with the threshold. So we believe that's the best answer. Cannot be is not a choice. Can be verified within for 1 and 2, but cannot be verified within the threshold for trial number 3. Well, let's check that out in a moment. Cannot be determined, well, because the experimental uncertainty, the data cannot be analyzed without more precise measurements. That's a false situation. We can always do that irrespective of the uncertainty. We could just be inconclusive. So for the third case, what we were looking at And I'll do that in red. For the third case, we have a velocity, a mass of 2 times a speed of 2.1 plus a mass of 0.9 times a velocity of -1. And then that would be equal to a mass of, combined mass of 2.9 times 1.1. And so this is 4.2, and this is minus 0.9. And 2.9 times 1.1 is 9 and 2 and 9 and 2 and 9 and 1 and 1 is 3.19. 3.19. And so what we end up getting here is we get 3.3 equals 3.19, which is 3.2. And we can see that is way more than the even 10% uncertainty. 10% uncertainty would give us 0.3 plus or minus 0.3. And it's definitely within that range. So we can confirm it we can rule out the fact that uncertainty is too large in case 3. We can verify it there as well. And so that's how we could completely and thoroughly handle question 11.